it's a pleasure to be here and to share with you our vision for a new approach to wind energy. The approach that we're pursuing is to develop wind energy technologies that match the reach of the wind itself, the global reach of the wind. And you can see that this is a tall order if you look at a map of the wind around the world, like you can see here. Those areas in red and in green indicate places around the world where the wind is sufficient to generate electricity. And so you can see that with the exception of the Western Amazon, Zaire in Central Africa, and then parts of Southeast Asia, the wind truly is a global resource. But despite the global reach of the wind, and in spite of the fact that today you often hear of wind energy as described to be mature technology, despite those facts, the reality is that wind energy today isn't coming close to having the global impact that it could. In fact, today only 4 countries in the world get more than 10% of their electricity from the wind: Spain, Portugal, Ireland, and Denmark. What I think is even more tragic is that there are developing countries like Ethiopia and Somalia that actually have very good wind resources, and yet some of the lowest electrification rates in the world. In many cases, fewer than 1 in 10 people having access to electricity when there's wind energy literally surrounding them. Now, part of the problem I see is in how we evaluate wind energy technologies today. There's always historically been a strong emphasis on what's called the turbine efficiency, basically telling us for the amount of wind that passes through in the denominator of this fraction, how much of that can be converted to electricity. And so people tend to, rightly so, look for turbines with high power coefficients or high efficiencies that convert a lot of that electricity into, a lot of that wind into electrical power. But what is less often emphasized, and what I'll introduce today, is a different concept, one called wind farm power density. In layman's terms, it's, let's say I give you an acre of land. This wind farm power density says how much power I can actually generate from the wind on that land. And what we'll see today is that an emphasis on turbine efficiency can often come at the expense of this parameter, this wind farm power density that we'll talk about today. Now, of course, at the end of the day, it's the bottom line that matters, how much the energy costs. And frankly, the reason we haven't seen a global reach of the wind is the fact that in many cases it's simply too expensive, wind energy technology. So this levelized cost of electricity, the cents per kilowatt hour, which includes how much the equipment costs to set up, but also the operation and maintenance of that wind farm, this is the important parameter we want to get to. And it's historically been assumed that if we can maximize this turbine efficiency, that's how we'll get to a decreased cost of electricity. But I want to convince you today that, in fact, the route that's more promising is to focus on wind farm power density, improving essentially the spacing of the turbines and optimizing that spacing. And so this might seem a little unusual, the idea of going from closer spacing to lower cost, but I'll try to step through the logical thinking here and how we can achieve this goal. So the idea, first of all, is that this closer turbine spacing will give us more efficient wind farms in the sense that that land on which you're building your wind farm is generating more electricity than it would otherwise. Because these wind farms are more efficient, we can actually generate sufficient power for our utility application or even powering a single home using smaller wind turbines than what are used today. So what I'll show you today is that, in fact, we don't need 300-foot structures to generate sufficient wind power. We can actually do it with turbines that are much smaller. Those smaller turbines, in turn, can achieve on a per-watt basis lower costs for the materials, for the manufacturing, which becomes much simpler, for the installation and maintenance, which now requires very simple equipment, things you can buy at your local Home Depot as opposed to specialized equipment. And ultimately, this is how we get to our lower cost of energy. So I want to step you through this process today and show you how this works. But again, I think it's worth taking a look at the current assumptions, because you can fairly ask, well, why hasn't anybody done this already if this is so straightforward? And so the usual starting point, and this really goes back even 30 years ago, is to ask about turbine efficiency. And the comparison that's often made today is between what's called a horizontal axis turbine, and I'll abbreviate that HAWT, which today can be around 100 meters, 300 feet tall, versus what I'll be describing as a solution in these vertical axis wind turbines, where the blades rotate on a vertical axis instead of on a horizontal axis. And these are going to be only 10 meters tall, about the height of the telephone poles that you drive by on the street. Now, if you were to ask what fraction of the energy flux passing through that swept area, so the circular sweep of these blades, in this case it's really a rectangular shape, what fraction is converted to electricity, invariably you'll find that horizontal axis turbines are more efficient individually than vertical axis turbines. And at that point, 30 years ago, people said, okay, well then this is going to be the platform we're going to use to develop our wind energy technology. Furthermore, as scientists, we like to figure out what are the theoretical maximums. What's the best that I could possibly do in theory in converting energy to electricity? And so this plot shows the answer at this horizontal line here at 59%. This is efficiency on the vertical axis versus tip speed ratio, or how fast the propeller blades rotate. The best efficiency limit, the theoretical maximum, is about 59%. And you can see here in green, this is the curve I really want to highlight, are modern horizontal axis wind turbines. So they actually do quite well. Modern horizontal axis turbines, the ones that GE, Vestas, and Siemens produce, are very close to the theoretical maximum efficiency. Again, a reason for people to say, well, let's just continue using these and maybe try to make them larger or maybe put them offshore. And the question becomes, is there really fundamental room for improvement in wind energy? And because many people assume there's not, the past 10 years have seen relatively little basic research in the wind energy area, aside from improving the reliability and performance of the existing platform. So we decided to take a different starting point and to question the basic assumption of what we're asking. And we start from what I call a wind resource utilization question. Let's imagine I have an entire wind farm. I'm not worried about an individual turbine, but I'm worried about that acre of land that you have that we want to collect wind energy from. And we ask, if we think of this as a volume of space, what fraction of the wind energy into that wind farm volume is converted to electricity? And it turns out that that's a different question from asking about an individual turbine, because as we'll see in a moment, the spacing of the turbine comes into play. Now, just for introduction, there's two sources of wind energy that are going to be coming into this farm. There's what I'll call a frontal kinetic energy flux. This is what you probably think of, the wind sort of blowing in your face past the wind turbine. And because of the friction at the ground, these arrows are meant to represent the speed of the wind. The wind is slower at the ground, and as you move up in altitude, the wind increases, so you get this sort of profile. But there's a second source of energy that only in the past 5 years has really received noteworthy attention. It's called the planform flux, and it's due to turbulence. So this term here, this U times W, is a measure of the turbulence in the wind farm. And what people have realized is that, in fact, that turbulence above the wind farm tends to draw energy down into the wind farm from above. And so this is going to be an important parameter for us to understand how to optimize a wind farm as opposed to a wind turbine, because that planform flux that's been shown in recent work by Johns Hopkins is actually the primary source of energy in a large-scale wind farm. So in a large wind farm, after the first couple of rows of turbines, most of that frontal energy has already been extracted by the first couple of wind turbines. What keeps most of the turbines in the farm going is that vertical planform flux through the top of it. And so we focused on that when we first started this work, and we proposed that, in fact, that's more important than the best limit that we talked about earlier. This is more important than the individual turbine efficiency for a couple of reasons. One is that if you actually go into detail, and maybe we can talk about this afterwards, in the best calculation, it says how much energy a single turbine can collect, but it doesn't say anything about what happens to the leftover wind energy. So yes, this turbine here didn't collect that energy, but there's leftover wind power here that I'd like to recover. In modern wind farms, in fact, the way that they design them, this wind power here is all lost. The turbines are spaced so far apart, and we'll see that in more detail in a moment. Another way to look at this is if you look at the front view of a wind farm. So the current work is really in optimizing that circular swept area, the path that those blades circle around. And the power coefficient there is typically around 50%, like I talked about earlier. But in between the turbines, but obviously there's no energy collection happening, and so the efficiency is effectively zero between the turbines. And so our thought is, well, instead of worrying about this 50%, and there's today billions of dollars going into moving this from 50 to 51 to 52%, we'd like to attach the big zeros in between there, because that's actually going to have a much bigger impact on the overall wind farm performance. So just to show you that what we can do in this particular study is to model that planform flux, and I won't go into the math, just to say that there are theoretical tools we have available in fluid dynamics to be able to predict that power that's coming into the top of the wind farm. So we imagine that we have this wind profile passing over wind turbines, and we have various modeling tools that we can use. The bottom line is the following, that in an 8 meter per second wind, this is about 17, 18 miles an hour, the type of wind that a wind farm would normally experience, The amount of energy that's going into the wind farm from the top is this number here, about 70 watts per square meter of land. So what this means is that for a square meter of the footprint of that wind farm, the amount of energy going into it is about 68 watts per square meter. So this number is important because then we can go back and say, how do wind farms today actually perform? Are they generating anything close to 68 watts per square meter? And so this data is available readily in various sources. I'm going to use a plot, and we'll step through this. This is a plot by a Caltech alum, David Mackay. And he put this together to look more generally at energy consumption around the world. So you have a logarithmic scale here, the energy consumption per person. So this is in kilowatt hours per day per person, and the population density of various countries and people per square kilometer. So you can see over here, Singapore would be a country that has a large energy consumption relative to its land size, the amount of area that it has available to it. Many developing countries like the Sudan, as you might expect, have relatively low energy consumption relative to their space, but these sort of comet tails here indicate the trajectories over the past 10 or 15 years. So you can see that these countries in general are increasing in population, but even more so are increasing in their energy consumption. Now, the reason that plotting this in this way is useful is that these lines of constant slope here indicate the performance of different renewable energy technologies. So, for example, energy crops, biofuels today will generally produce about a half a watt of power per square meter of land area that you're dedicating to growing those biofuels. Again, that's a half a watt compared to the 68 that I talked about on the previous slide. Wind power actually isn't that much better, and this is the important point on this slide. Wind power today generates about 2.5 watts of power per square meter of land area on those wind farms. And that performance is in fact so limited that you can take a country like South Korea, which sits above this line, and the interpretation here is that because this dot is above the green line, I could cover the entire landmass of South Korea with current wind farm technology and still not generate enough electricity to power their needs, to satisfy their electricity needs. And of course, the danger is that as these countries continue to rise up and go to the upper right, our research should hopefully better start pushing to the upper right as well. For reference now, we can look at that calculation I just showed you. This is what's actually available to us if we could redesign our wind farm, that 68 watts per square meter planned performance plus. So there's a huge performance gap here with current wind farms. And this is sort of the take-home message initially here is that, yes, individual wind turbines have power coefficients that are actually close to the theoretical limit, but the wind farm performance is still far below the maximum performance. And so you could ask, why is that? And I think this picture sort of answers that question. This is a photograph, an actual photograph of the offshore wind farm, the Horns Reef wind farm in the North Sea. They happened to take this on a day where, because of condensation, you can see very nicely the wakes that are being produced by these turbines in this array. And hopefully you can see there's also turbines in these rows behind them. The turbulent air that's created by each of these wind turbines impacts the performance of its neighbors. So these turbines here are working at maximum efficiency, close to that 50% power coefficient. But because they end up disturbing the air that then goes into the neighbors, all of these turbines suffer in performance. They perform much worse. And so today's solution is simply to put the turbines as far apart as possible in order that they don't have these interactions between one another. But again, what that means is that there's these alleyways within this wind farm where no energy is being extracted, where this wind farm is not producing electricity in order to preserve the individual wind turbine performance. So we can actually quantify this and see how this actually impacts the performance, this turbine spacing requirement. I showed you on the previous slide a 2.5 watts per square meter is the typical performance, and that was based on measurements of actual wind farms around the world. Another way to get that number is to imagine you're looking from a bird's eye view on one of these horizontal axis wind turbines. And so we can imagine there's some circular region around that turbine where I can't put another wind turbine to avoid those aerodynamic interferences. And so we can calculate the power density if I know the rated power. Let's say it's a 1 megawatt wind turbine. But we multiply that by what's called the capacity factor. Basically, on average, the turbine's not going to be running at max. It'll run at maybe 30% of its maximum because of the fluctuations in the wind over time. And so this capacity factor will be 30%, let's say. And then we know the turbine diameter, which might be 100 meters, 110 meters, and the turbine spacing. And we put all of that together, and we can calculate this for actual commercially available turbines. So I didn't list them by name here, but this is a GE turbine, 2.5 megawatts. This is a Vestas B112, 112 meter diameter. And you can see plugging in there, we get numbers similar to what we saw on the previous page, 2 to 3 watts per square meter. Now, if we could put them down to 4 diameters, we already would see how this power density would tend to increase. We'd more than double them just by reducing the spacing by 50%. And again, it has to do with this square dependence of the turbine diameter. Of course, in the case of the horizontal axis turbines, if we were to actually reduce them to that 4 diameters, the performance would nosedive because of those wake interactions that I showed you on the previous slide. So this is a real challenge. On top of that, in actually implementing wind energy, making a global impact again, there are other challenges that you're all familiar with. The issue of the size of these turbines relative to our sort of natural scale of metropolis. So here's a utility pole, transmission tower at 125 feet. This is a scale drawing of a large 2.5 megawatt turbine. So because of those the relatively large scale here, this increases rather the design requirements. The engineering materials required to build a structure that's safe at this size with blades that are undergoing centrifugal forces, gravitational forces, wind loading is enormous. And this, of course, drives up the materials cost and the cost of the technology itself, the cost of the energy. Installation and maintenance can be a big challenge. This is a picture I found showing a caravan. Sometimes you'll see these caravans in California here. The blades are getting so large that now the maximum size of the blades is really dictated by our freeway system in the United States. The ability to go underneath an overpass is limiting the size of these. And there are efforts to maybe build the structures at the site, but then you have to contend with the weather, and in general, those things raise the cost. If you think about offshore wind farms, you can imagine now that instead of driving on a road, you're floating on a barge, and the complication increases, as does the cost. And then there are issues that you might say are subjective, but nonetheless can impact your ability to get a permit for a wind farm. The concerns about impact on birds and bats, especially here in Northern California, the Altamont wind farm, this has been a very serious issue, where in many cases, the birds simply don't see the blades because of their high rotational speed, and so they can be killed by the blades without even noticing that they're in danger. The visual signature, you could say, is objective. You know, as an engineer, I think all wind turbines look really cool, but not everyone agrees with me. And again, that can impact the ability to get a permit. There's the issue of acoustic signature, the noise that these turbines create, which is increasingly leading to a lot of municipalities simply not allowing wind turbines to be installed. And then more recently, there have been issues with radar signature. As these turbines get larger, the sweeping blades can actually interfere with the radar capabilities of the military or the FAA. And so that's, again, placing another constraint on where these turbines can be installed. As far as the bigger picture, the current paradigm for wind energy is really just not applicable to the developing world. The infrastructure required, it just makes it not feasible to try to install some of these wind farms in some countries where they simply don't have the transmission to send a megawatt of power or 10 megawatts or 100 megawatts of power across their lines. And so for all of these reasons, we wanted to pursue a different approach, one that we thought that I'll show you in a moment, demonstrate improves the efficiency, but also deals with many of these other challenges as well. And that is to replace the few large monolithic horizontal axis turbines with arrays of smaller vertical axis wind turbines. So the advantages are many. First of all, smaller structure size, which leads to lower materials costs, lower visual signature, lower acoustic signature. The turbines are simpler in terms of logistics of installation and operations and maintenance. So there isn't the need for a lot of the specialized equipment that you need today to install wind farms. Scalable from distributed power, a ranch that needs to generate 10 kilowatts, to utility power, where you'd want to generate hundreds of megawatts. And then again, safer for birds and bats for two reasons. One is, again, they're lower, so they're below the flight corridor of most migrating birds. But also the blades rotate more slowly than on these horizontal axis turbines. So the visual signature is different and one that birds can avoid. And so, in fact, of the dozen or so companies that produce these worldwide, there's never been a reported bird strike from any of these companies. So this is a demonstrable benefit. Now let's go back and think about the power density very briefly. Now we're looking at a bird's eye view of a vertical axis turbine, where we have the rated power, the capacity factor. And here's an off-the-shelf turbine that we use for our research. The individual turbines, of course, are much smaller in their power rating. So instead of megawatts, you're talking about kilowatts, but you're also talking about much smaller structures in terms of the size of the structure. And so if you calculate the power density like we did before, assuming the same spacing, same capacity factor, immediately we already get to almost 3 times the power density of the current technology at 1/10 of the height of the structure. A much smaller structure generating a higher power density in terms of this calculation that we show here. But I think it's useful to, numbers sort of can maybe not sink in. Let's think of an actual comparison. A 150 megawatt wind farm is something that could be produced today and pretty reasonably. Let's say we wanted to do that with an off-the-shelf 1.5 megawatt turbine versus, and I'll use a 3 kilowatt example for reasons that I'll make clear later on. But again, something much smaller, but a vertical axis turbine. So to generate that 150 megawatts, you can see a huge difference in the number of turbines. You can do that with 100 of these horizontal axis turbines. You need 50,000 of these here. Immediately, this, though, gives us a couple of benefits. One is the unit cost going down because of mass manufacturing. It's a much different modality for how you're producing the turbines, almost like the auto industry, where you have a line of these being generated, rather than these being essentially handcrafted one at a time. So the unit cost can drop significantly. But the thing I want to point out is the wind farm footprint. So you might say, wow, that's 50,000. But these 100 turbines will take an area of 77 square kilometers, size of a whole town in some cases. Whereas for that same spacing, these turbines only use up 18 square kilometers at this spacing, again, because of the higher individual power density of the turbine. But what's more is this is all assuming 6 diameter spacing. What if we could put them closer together? If we do 4 diameter spacing, we know we can't do that in this case because of the aerodynamic impact. What I'll show you in a moment is we can do this, and now we're down to 8 square kilometers as opposed to 77 for the same amount of power. Or you could split this, of course, and that acre of land that I gave you, we'd make it something much bigger, a few 100,000 acres. I'm going to be able to get almost a factor of 10 more power out of that land that I gave you using this approach versus the existing one. Again, using structures that are a tenth of the size, that are lower cost, and so on. And so this is really the place at which we wanted to begin studying this problem and to start asking, okay, how do we optimize these vertical axis with turbines? How do we find the optimal arrangement? As I said before, the horizontal axis turbines, the optimal arrangement is as far apart as possible. But in this case, that's not going to be the case. We went to our toolbox of methods that Cindy mentioned earlier, bio-inspired engineering. We believe, and we've shown that in nature and biology, there are actually lots of natural solutions to a lot of the problems that we think about as engineers. And so in my lab, we've done a lot of work studying jellyfish, and we've used them to design more efficient underwater vehicles, to develop diagnostic tools based on the blood flow that are similar to diagnostics of swimming performance in jellyfish. And so we wanted to see whether we could do something similar, look to the aquatic world to find an answer to this question on optimality of these wind turbines. And so the specific inspiration that we look to is fish schooling. So you've all seen on television programs, or if you're a scuba diver, maybe you've actually been able to see this yourself. These fish swimming in these very regular arrays. The spacing between the fish as they move is quite regular. And you can see if you're not one of the bunch here, you sort of get washed away. So it's been shown that these animals swimming in a school are able to swim cooperatively, in the sense that the energy that this fish uses to go from point A to point B is less than it would be if it was swimming by itself. It uses the interaction with the flow of its neighbors in order to improve its performance. And so this was conceptually the analogy we wanted to make. Instead of having a fish that's flapping its tail and creating these vortices, we imagine from a bird's eye view now, the wind blowing and generating the rotation of those vertical axis wind turbines. So the first conclusion that it suggested to us is, well, maybe these shouldn't all rotate in the same direction. Some rotate clockwise, others rotate counterclockwise. And we've shown that that actually does make a difference for the performance. But it turned out we actually had a ready-made solution already at Caltech. So we went to the library and found, here you can see Ted Wu, Charles Brokaw, and Chris Brennan. These are all Caltech professors who were working in the mid-'70s on the fish schooling problem. And so they had already developed an entire mathematics for optimizing the position of these fish, and so we ended up using something similar to optimize the positions of turbines in a wind farm. And so this was Danny Wise, one of their students back in 1975. You can see here now from a side view, or wind going from left to right, I should say, still from a bird's eye view, the types of patterns that we wanted to study. And the question was, using these numerical models, can we predict what sort of improvements in performance we would get for this approach versus the conventional ones? So this is a bunch of data, so I'll step through it. What I'm showing here on a log scale, again, is the rated power density, so we're not including the capacity factor. And here's the data from some operational wind farms around the world. And here were the hypothetical data points for a variety of vertical axis wind turbine farms. And so the model was predicting an order of magnitude increase in the power density, a factor of 10 improvement in the performance of these wind farms by using this fish-inspired arrangement of the turbines. And so we thought this was, a really fantastic result, and we put it in the journal Bioinspiration and Biomimetics a couple of years ago. And of course, the response was typically, oh, this is a clever idea, but does it actually work for real turbines? And so this is the stage at which a lot of academic ideas tend to die, because the challenge is that we could do computer modeling, in our labs. We can get funding from NSF and so on to be able to do something like that. But a computer model at the end of the day still requires empirical data inputs to know that what you're simulating on the computer actually matches the real world. We have great wind tunnel facilities, but that would be on scale model turbines, and so you still get the question, yes, this is interesting for a wind tunnel, but what happens if this is at full scale? And in neither of these cases can we replicate natural wind conditions. One of the things that was learned in the sort of the first or maybe second boom in the 80s in terms of wind energy is that a lot of predictions people made in wind tunnels simply didn't hold up when you put them out in the real world. And so this was a place where it was sort of, well, is this going to be the end of the story for this? And so the reason we were able to take the next step was really because of foundations like the Moore Foundation, who were able to allow us to really pursue a revolutionary experiment, which was to actually build these turbines at full scale in the field. And so we established this Caltech field laboratory for optimized wind energy. This is a photograph of the site. This is in the Antelope Valley, just a couple of hours north of the Caltech campus. And so hopefully you're saying, well, so where are the turbines? So they are there. And this is sort of to emphasize that reduced visual signature. So you have this very nice landscape that we wouldn't want to mar by having very large horizontal axis turbines sort of rotating in the distance. So this is at that 10 meter, 30 feet sort of height. And originally we only had 6 of these turbines. And so you can see in this video here what the site looked like. That's me for scale there. And so what you're seeing is a little remote control helicopter flying through the site with a camera. And so what we did initially was we had a couple of these turbines on sort of Christmas tree legs here. We're moving them around. You can notice how closely spaced we have these turbines in these different cases. And we're measuring the power that they produce in different arrays, by themselves, in 2s and in 3s, and trying to determine whether we can actually verify those predictions that I showed you numerically in the computer model. And so we studied quite a few. I'll show you data for one staircase sort of arrangement that's close to the fish school inspired arrangement. Now, the turbines here are spaced by 4 diameters, which is closer than what you would get in the horizontal axis turbine. And the first result we found was that the closer we put these in pairs anyways, that actually ended up increasing the efficiency rather than reducing it, as you see in the horizontal axis case. So a very different result from what you get in the case of the horizontal axis turbines, where, again, reducing to 4 diameters would reduce your efficiency by 20 or 30% typically. But what we were really after was this power density, and this is the measured power density at the site, plotted against this plan-form kinetic energy flux. Think of this, again, as just how much energy is actually going into the wind farm to begin with. This dashed line here is at 2 to 3 watts of power that existing wind farms produce. And so we measured over 250 continuous hours in 2010, and here's the data. So the black dots are really the ones that are the most direct comparison, because this is the continuous power, meaning if the wind cut out for hours at a time, we just average zeros into the record. So we're not trying to bias the result toward only when the wind is blowing. Even in that record, we see substantial improvement over the performance of existing wind farms. Now, if we only look at the times when we're above cut-in, meaning the wind is high enough to actually cause the turbines to rotate, you can see for each of the days here, so these data points match up vertically here for different dates in 2010. You can see that we're able to get much higher, very much closer to the actual performance or the flux limit that I talked about earlier, that 68 watts per square meter. So this was our first real result here, and actually got quite a bit of positive response. And aside from the efficiency, one of the feedbacks we got the most was from people who would see this in the news and say, we're actually excited about wind energy in a place where it's environmentally sensitive. I live in Hawaii, or we're in the Blue Ridge Mountains, and we really like our scenery. We want to support green energy, but at the same time, we don't necessarily want to sacrifice some of the natural beauty of our area. And so that was one of the telling responses that we got that said that maybe we were on the track of something that would be useful. But nonetheless, there's still the yeah buts, the common question, yeah, this is interesting, but. And so the next stage was the question, well, what happens if it's a larger array? That was only 6 turbines. What happens if it's a larger sized array? Will the wind just pass around it instead of through it? And so again, with more funding, we were able to actually pursue this at full scale with 18 of these turbines over this past summer. So this video shows you what the site looked like as of last summer. Again, there's need for scale. And so now this baseline configuration we were looking at is counter-rotating pairs of these vertical axis turbines. You can see in black here, we have 72 different stumps, if you will, where we can put these turbines. And the question is simply, what's the optimal configuration of these turbines? And then we want to be able to measure the wind flow through this array to actually see how the performance of this system varies from the case of 6 turbines now to 18 of these turbines in this array here. So what we did in order to answer that, here's a picture of us, sort of our Iwo Jima sort of picture here, raising the flag. We have the 7 wind profilers here, and we're measuring, so we're raising this and we're measuring at different locations the wind speed. And again, the important question here is whether the wind is actually going to pass through our array or if it's just going to somehow pass around the array. And so what we did now, looking at sort of a blueprint, this is due north, our prevailing wind is from the southwest, and so we have these 18 turbines in this array, and we measured along this green line, straight down the heart of our little array, and we wanted to measure wind speed. And so these are the results here. So again, this wind speed here is in meters per second. This is downstream distance from the rotors. These lines here are positions here, here, and here. And so you can see what you would typically expect in this type of a data set, where the wind up front is going to be the highest. It decreases as you get towards the array. And then each time you go past one of the turbines, it's extracting energy. So the wind speed goes down, and then it recovers, and then it drops down, and then it recovers, and then it drops down, and then recovers again. And so this data set tells us actually quite a bit. So first of all, I'm just going to normalize this. So all this data now, the wind speed is just normalized according to a value of 1 for right in front of the array here. So we do see some blockage effect here. So the wind far upstream is about 15 or 17% higher than the wind speed at the front, which we expected. But the thing that's encouraging is that by the time we get to the third row, we've sort of leveled out to a steady state, what we call an asymptotic flow. This is consistent with what you see in even horizontal axis turbine arrays, where they're trying to space them out as far as possible. So even in that case, they usually don't see a steady state behavior until the third row. But now, because we've been able to measure that asymptotic flow in the real world, we can take our data from this back row and estimate what would happen if I had an array of 10,000 of these turbines, because those 10,000 turbines would all have the same type of asymptotic behavior. And so the power density that we get based on that third row measurement is 11 watts per square meter, which already is 4 times what we get from the horizontal axis wind turbine farms. And this is before we've done any optimization. So this was just that baseline configuration that we picked to start with. What we're doing now and next summer is to start optimizing and basically going up from this result right here. Now, there are still, of course, many unanswered questions that we need to address. First of all, how do the aerodynamic interactions within the farm lead to the performance that we're seeing? So we sort of treated this as a black box so far, and we have this result that says the performance is improved, but why does it actually happen? So there's been work recently looking in CFD, or computational fluid dynamics and experiments, and in this case, we just imagined 2 counter-rotating cylinders. And so at low tip speed ratio, the low rotation rate, The idea here is as a model for a bird's eye view of these vertical turbines. You get this buffeting, this turbulence that's created in the wake, similar to what you saw in that previous picture. As I increase that tip speed ratio, you can see that that wake is suppressed. And so we think this is the mechanism, the interaction between these counter-rotating turbines that's able to suppress that wake shedding, which then gives cleaner air for us to put another set of turbines closer together in this array. To verify that, we've developed a technique we call snow particle image velocimetry. So the velocimetry just means we're measuring the air velocity. We're doing that by optically using a camera or video measuring particle images, and the particles are snow. So we teamed up with some friends from Hollywood, got some snow machines, and took them out to the desert, the high desert in the Antelope Valley. And so we shoot snow into these turbine arrays, and then we measure how that snow is carried, and we create these velocity maps. And so they're starting to confirm this picture for us. But this is just a bit of technology development that's come along the way. The other questions we need to ask are how we can take advantage of the canopy flow analogies. A lot of what we're studying has been studied in the context of forestry, actually, how wind passes through forests. And so we'd like to use a lot of that knowledge base in order to not only optimize the turbines, but also to design turbines that are more gust resilient. So one of the things that's a challenge for a turbine is that you want to collect as much energy as possible, but you don't want that same energy to destroy you at very high wind speeds. And so the best example of a structure that does that is a tree, as far as the gust resilience. And so we're using some of the knowledge in terms of material science to improve designs of turbines. The other question, and this is really goes to the heart of having this real-world impact, is how we can leverage the smaller size. The physics of the problem says that a 10-meter structure can be built with much less expensive materials, wood, for example, than is possible for a 100-meter structure. You simply can't build a turbine at 100 meters out of wood because the fiber stresses simply won't support the loading. So things like that can reduce materials costs in a way that's fundamentally different at 10 meters than it is at large scale. Operations and maintenance. Again, at our field site, we can operate and maintain these with a step ladder, as opposed to having the specialty lift and crane equipment that's required to maintain the very large turbines. Again, environmental impact comes into play because of less materials overall. Energy storage is something maybe I can comment on at the end. There's opportunities, rather, to optimize the power delivered by these arrays when you have 50,000 agents generating power as opposed to only 100 agents. And so there's some interesting algorithms we can take advantage of, and ultimately reducing the cost of electricity. And again, the model that I see is very much like the auto industry. I see this as being the potential to be an entirely new manufacturing base in the United States, where at the height of the auto industry, we were producing 10,000 cars a day. So these turbines are very much less complex than one of these automobiles in terms of the guts, basically a generator and maybe a control system. And so even if we imagine that there was a one-to-one correspondence and we were producing 10,000 of these turbines a day, that's translating to hundreds of megawatts of power that we could be producing on a daily basis. And so it would very quickly ramp up the contribution of wind energy to the mix of consumption here in the U.S., not to mention the opportunities for other countries, developing countries, to have a low-cost energy source. So where we are today is sort of at this stage here, where our research, and we're continuing to understand this trajectory here, but we've been able to demonstrate down to this point here where now the challenge is for the individual turbine to demonstrate lower costs. The turbines that I showed you in the videos and the ones we've been using for our research are frankly too expensive for use in this model, in part because the companies that are designing them haven't had cost as their primary impetus. It's really been for what's sometimes called eco-bling, the idea that you have this green structure that sort of looks nice, you put it out in front of your building and you can say, hey, I'm green, but it's only, maybe powering the front light of the building. So we want to develop technologies that have a meaningful contribution, and that means the cost has to go down. And so this is where we're making our transition from the lab to the real world. First of all, is in commercialization of a low-cost vertical axis wind turbine. So I've been privileged to actually work with Anant Natarajan, who's here, and Joe Yang, and we're sort of keeping it in the Caltech family in a sense, and developing a startup company to commercialize the first real low-cost vertical axis turbine, and the model that we think will be for the future of this type of work. And so in summer 2012, we'll start to begin field testing this particular design. Now, the other aspect that we're really excited about is the real-world implementation, and we have a real opportunity in a collaboration with the Keck observatories to demonstrate this approach to wind energy in a place where it really fits well. Hawaii, as you may know, the Big Island in particular, is a place that's environmentally sensitive. It's a place where currently the commercial cost of electricity is several times higher than it is here on the mainland. And so this is an opportunity for us to be able to use the local wind resource in a way that's environmentally responsible. So first of all, we're starting a one-year pilot wind study with the Keck Observatory's headquarters in Waimea to study the winds over the next year and to determine exactly how we would be able to generate, or how much power we would be able to generate. And we're also looking at possible opportunities for turbine testing elsewhere on the island. But again, the idea here is that we've been fortunate at our field site to prove out the scientific aspects, and now we want to add the business logistics to show that there really is a business case for this approach, and we see this as being a great opportunity to do that. So finally, let me just make a few acknowledgments. There's been many students who've worked on this project. As the alums in the audience know, Caltech students are very smart, and so we've been very fortunate to have graduate students and undergrads working on various aspects of this project. As I mentioned before, the Moore Foundation has really been instrumental in taking this from an academic idea to something that has the potential for impact in the short term. You know, many of the things we work on as academics have more of a 10 or 15 year sort of pie in the sky time frame, and this is a project where really in the next 18 to 24 months we think we can see real impact on the ground, and that's going to be in large part because of the investment of the Moore Foundation. I should just mention and direct you to our website, where not only are we studying wind energy, more generally this effort is supporting work in flow control, trying to improve aeronautics and micro air vehicle design, propulsion, and again, biomedical devices, all with this synergy between physics and biology and mathematics. And just one last note on this particular program in wind energy, the field laboratory work I've described is really just one piece of it. We have quite an extensive wind tunnel research activity, computational design, and materials and manufacturing. So it really is a large-scale effort, and it's going to require a large-scale effort because, again, we're fighting against the status quo that says that the problem's already solved. And so first we have to convince people that there is a problem to solve, and then demonstrate that we have an approach to solve it. So with that, I thank you for your attention. It's been a pleasure to be here, and I'd be glad to take questions.